This video is going to cover antiderivatives and integrals. Okay, so antiderivatives are just the inverse operation of a derivative, and integrals we'll talk about a little bit of the vocabulary and kind of what each one of those means in a minute. But for the target, students will determine the antiderivatives of a function using inverse operations and integral rules to determine the general solution. Okay. So let's kind of talk a little bit about what we already know and then use it to find things that we don't know. So it says, suppose we find f of x. Anytime we use a capital letter to represent a function, and that's going to be a really big important thing here. Anytime we use a capital letter to imply functions, that means we're talking about that f of x is the antiderivative of lowercase f of x. So we use capital letters for function notation to represent antiderivatives. Okay, so if we think of f of x as 3x squared, what would we have to take the derivative of to get 3x squared? So we're going to start thinking backwards, kind of going from the derivative to the actual function, or from a function to the antiderivative. So if we think about that, if we take the derivative of 3x squared, or if we've taken a derivative and we get 3x squared, that means our f of x was possibly x cubed. Okay, so that could be because if we take the derivative of x cubed, we get 3x squared. So it makes sense that the inverse operation to get back to the original would give us that x cubed. But that's just one function that it could possibly be. There could be a whole bunch of different functions. Like we could have started with x cubed plus 1. We could have started with x cubed minus 7. We could have started with x cubed minus 347. The point is, there's a value there that we don't know that could have possibly been zeroed out during the derivative process, some constant value. So when we think about that, just in case there was a constant value, we add this plus c. We call this the constant of integration. That's not how you spell constant. Okay, so the constant of integration. Okay, where f of x, capital F of x, represents the antiderivative. So the idea of going backwards is just doing it in inverse operation. So if we wanted to do a plus, we do a minus. If we wanted to do a multiplication, we'd do division. It's just inverse operation. So the antiderivative is just the inverse operation of a derivative. Okay. So if we think in our derivative process for power rule, the first thing we did was multiply the exponent and coefficient. I'm just using some abbreviations for short. And the second thing we did was subtract. Second thing, 1 from the exponent. Okay, so if we think of the inverse operation, we're kind of working backwards. So instead of starting at 1, we'd actually start at 2. And instead of subtracting 1 from the exponent, we would add 1 to the exponent. And then instead of multiplying, we would divide by that new exponent. So kind of working backwards of what we did with derivatives. Okay. So instead of always writing what would the function be, what would to have a derivative f of x, we use this notation. So this symbol is the integral notation. It's an elongated s, okay? And the way we read it is the integral of f of x with respect to x. Now this piece, that dx, is part of our derivative process. Remember, we get dy dx. Okay, so we wind up separating these two and adding our dx to our function. But that dx is pretty important because just like in our derivative process, this told us what our independent variable was, what variable was changing in our process. The same thing goes for this. This is going to tell us the variable of the problem, because there is a point where we can take an integral that has multiple variables, but only one variable of integration, which most times is an x, sometimes a t. Okay. And when we do that and we get this, we find this antiderivative, we call this the general solution. So I think issues writing today. Erase that really quickly. Get a thinner pen. That might be better. Okay, so we call that the general solution. And every general solution has this idea of a plus c. Okay, this integral looks like an elongated s, and that's not an accident, because when we figure out how to actually find integrals, then we'll see that it's just a summation. So s being sum, elongated s being, that's exactly what it represents. And we always write a plus c after our integrals process. Now the difference between antiderivative and integrals, very much like the difference between derivative and instantaneous rate of change. Remember, derivative gave us the equation that led us to slope. Once we plugged in a value and we got a numerical value in response, that became the instantaneous rate of change. So one being an equation, one being a value. That's kind of how antiderivatives and integrals work. Sometimes we call the antiderivative an indefinite integral, and that's because the integral represents the numerical value we get as part of an integration process or an antiderivative process. So they're kind of pretty much the same thing. One represents a number, one represents an equation. Same thing with derivatives and instantaneous rate of change. Okay. So some basic rules, just like with derivatives we had basic rules, with integrals we have basic rules as well. So I'm going to scroll this up. Okay, if we're taking the derivative of 0, we get a constant value. Or sorry, if we're taking an antiderivative of 0, we get a constant value. So that's number 1. Because we know the derivative of a constant is 0. So kind of working backwards. If we have just a value of k, like 4 or 7 or 9, we know that we're going to get kx. And then you see that plus c. Every integral is going to have a plus c. In fact, the antiderivative, the general solution is incorrect if it doesn't have the plus c. We put that in case the c was not 0 as part of the original function. Okay, but if we think about this, if we have k, the integral of kx, there's really an x there. Remember, just all the things we talked about with derivatives, it's going to still apply. So if there's no x, there's really an x there. It's just a 0 power. So if we add 1, that becomes 1. And that coefficient, just like everything we've talked about, our coefficient just comes along for the ride. It doesn't change in a process. In fact, we can take it out of a process, just like we did with derivatives. We ignore it until we need to use it to multiply it by something else, or simplify it in this case. And then, of course, that plus c as a result of that rule. Okay. The next one is kind of what I was just talking about, that coefficient, the idea of taking our coefficient, so k is a coefficient, and taking it outside of our process. Well, that's terrible. So taking it outside of the process, and then worrying about the function piece and dealing with the coefficient later. Okay, just like with derivatives, we have products and sum rules. So that's not a product and sum rule, sorry. Sum and difference rule. And just like with derivatives, that just tells us that we can take the derivative or the integral of each piece of the problem independently and bring them back together with plus and minus. And then that power rule that I was talking about. Okay, it's the exact opposite of the power rule for derivatives. So instead of subtracting 1, we're going to add 1 to our exponent, and then we're going to divide by that new exponent. Okay, so the inverse operation of all of what I wrote here. Okay, so all we're doing is the opposite of that because we're undoing the derivative process. Okay, so let's look at an example. So if we look at this one of the rules says that I can take out the 3, okay, and then deal with the x on its own. So right now my power is 1. So the rule says, bringing down my coefficient, to add 1 to my exponent, so that becomes 2, and divide by that new exponent. And then add a plus c. We always want to do that. So if we simplify that, we get 3 halves. Remember, I like my coefficients in front, plus c. We get something like that. Something simple. All the properties we talked about and all the strategies we used during derivatives are still going to apply. So for b, power rule only applies if our variables in the numerator, same thing as for our derivative power rule. So the first thing I'd want to do is bring up that x by negating its exponent. Remember, negating changes position. It reciprocates. Then I can do my integral process. So my coefficient is 1 right now, so I'm not going to worry about that. When I add 1, I get -2. Divide by -2 and add a plus c. I always want to put it back into the form that it was originally in. Okay, I don't want negative exponents, so I'm going to move my negative in front because my whole term is going to be negative. I'm going to have a 1 in my numerator because I'm going to push that x to my denominator. And then a plus c. And there's my antiderivative. For c, what we want to do is, again, rewrite, put it in power form to get that. When I take my antiderivative, I'm going to add 1 to 1/2. So that's going to give me 3 halves. And divide by 3 halves, the new exponent, plus c. Now dividing by a fraction means we're multiplying by the reciprocal. So I'm just going to multiply by the reciprocal, that's my new coefficient, and put it back into the form that it was in when we started. So square root, because that's my power, x cubed, that's my exponent, and then plus c, and I'm done. If we can simplify up front, we want to simplify up front, like d. So if we go here, first thing I'd want to do is rewrite x to the 1/3, x minus 4. We do not have a product rule for integration, so I can't integrate a product right now. So I'd always want to get this into power form, which is just an easy distribution. So let's distribute this x to the 1/3. So remember, this is x to the first. So when we're multiplying, we add our exponents. So we get 4/3 as our exponent minus 4x to 1/3, and then dx. Now I'm ready to actually integrate. So we're going to add 1 to our exponent. So this is going to become 7/3 over 7/3 minus, here's my 4. I'm going to add 1 to 1/3, so 4/3 divided by 4/3, and of course a plus c, always. So I want to simplify this a little bit. So dividing by 7/3 is the same as multiplying by 3 over 7, putting it back into root form, so the 3rd root of x to the 7th minus, now multiplying by the reciprocal, so 4 times 3/4. So 4 times 3/4. So that's over 1. That's going to cancel out, and we're going to be left with 3. So our new coefficient is just a 3 here. 3rd root of x to the 4th, and then a plus c. So I'm going to draw a little line because I know this problem maybe kind of went into the next one. Okay, so I'm going to do F before we go to E. So again, I don't have a chain rule, I don't have a product rule right now, so the only thing I can do is put it into power form. So I could easily distribute this, not distribute, but distribute out the x squared plus 1 times x squared plus 1. So if I integrate, if I FOIL it out or distribute it out, I'm going to get t to the 4th plus 2t squared plus 1 dt. And then it's in power form and I can apply my power rule. So if I add 1, I get t to the 5th over 5 plus 2, remember just bring the coefficient along, t cubed over 3 plus, remember here's a t to the 0, so 1 t to the 1st over 1 plus c. And then I'm just going to rewrite it. I don't like my coefficients mixed, I like my coefficients in front. So I'm going to rewrite it 1/5 t to the 5th plus 2/3 t to the 3rd plus t plus c. Okay, and remember we can always check if our process is right by taking the derivative. If we take the derivative, we should get back to where we started with is what this is. Okay, so we can always check